All right, we're going to review indeterminate forms in Lapital's rule. Lapital's rule is a way to evaluate limits by getting it, or if your function makes one of these two indeterminate forms, either 0 over 0 or infinity over infinity. It could end up being positive or negative infinity when you're doing that, but you have to have one of those two forms. What we figure out is if you have one of those forms, then your limit is equivalent to the derivative of both the top function and the bottom function, finding the derivative of both. It's not using quotient rule. You just simply take the derivative of the top function, the derivative of the bottom function, and then keep evaluating your limit. Let's try one out here. So find the limit as x goes to 1 of natural log of x over x minus 1. We can see right now if we were to plug in 1, we get 1 minus 1 is 0 on bottom. Natural log of 1 is also 0. So right away we have this indeterminate form of 0 over 0. So what our next step is now is to apply Lapital's rule. We want to, one, indicate that we're using it. One way is just put the little LH over the equal sign and then still write your limit notation. And then we're going to take derivative of both top and bottom. So derivative of the top of natural log of x is 1 over x. Derivative of the bottom is just 1. Now there's no problem with plugging 1 into this. We can evaluate and get our answer. So if we plug in 1 now, we got 1 over 1, which would equal 1. So this limit would approach 1. Let's try another one. Calculate the limit as x goes to infinity. So right now, if we were to do infinity and put infinity in there, e to the infinity power is going to get very large. Infinity squared is going to get very large. We have indeterminate form here. Of infinity over infinity. So first step, again, we're going to take derivative of both top and bottom function here. So derivative of the top is still e to the x. Derivative of the bottom is 2x. Now if we plug in infinity, we still have infinity on the top. 2 times infinity is still going to be very large. We still have this indeterminate form of infinity over infinity. So what we need to do then is apply it the second time. As long as you have indeterminate, you can keep doing Lapital's rule here. So derivative again would be e to the x. On bottom, we just get 2. Now we do not have infinity over infinity. Top's still going to go to infinity. Bottom's just going to be 2. Infinity divided by 2 is just a very large number, so this limit is going to go to infinity. One way to kind of see that too, just looking up here, which function's kind of going to win out or get large faster. Something to an infinity power is going to go up faster than infinity squared. So that's why we know that since the top's getting bigger faster than the bottom, that this probably will keep it getting big. All right, next one, calculate the limit as x goes to infinity here. So again, you got to check, do we have indeterminate form? Natural log of x, that graph looks like that. So yeah, as x keeps increasing, this is going to keep increasing. Cubed root of x, if you cubed root of infinity is still very large. That graph also kind of looks something like this where it is increasing. So we got 2 increasing ones. What's going to increase faster? So again, we have indeterminate form here of infinity over infinity. Let's apply Lapital's rule. So top is 1 over x and bottom. Probably want to think of this as x to the 1/3 when doing derivatives. So bring down the 1/3, new power is x to the negative 2/3. All right, now on these types of problems, what you want to do before checking this again, since we don't have that natural log in there now and everything's a polynomial or rational expression there, try to simplify first. So on this one, we know if we have a negative exponent that's the same as 1 over 3x to the 2/3. Let's multiply by the reciprocal here, both top and bottom. If you want to put over 1, you can. So that cancels. So what we're going to end up with here is what's the limit? As x goes to infinity of, this should simplify here. If we got 3x to the 2/3 over just x, or x to the first, remember you can subtract those powers, so this will end up being the same as just x over, or 3 over x to the 1/3 power. All right, so now let's check it. As this goes to infinity, we got 3 over a large number. What's that going to go to? This one's going to approach 0. This one's going to go to 0. All right, a little bit of a different one here. This one's got some trig in there. There's also 2 things being subtracted on top, but let's see what we get. If you do tangent 0, that is 0. So this is all going to equal 0. That's 0. That's 0. So we do got the indeterminate form here of 0 over 0, which means Lapitals can be applied here. So let's apply it. So the derivative tangent is secant squared. Derivative of x is 1. Derivative of the bottom is going to be 3x squared. What do we get now if we plug in 0? Secant squared, remember that's secant's the same as 1 over cosine. So what do we get if we did 1 over cosine squared? Well, cosine of 0 squared. Cosine 0 is 1. And so we'd have 1 over 1 squared, which is 1. So on top here, we got 1 minus 1, or 0. On bottom, we still got 0. Looks like, again, we got to apply L'Hopital's the second time here. So let's do it a second time. Derivative of secant squared. We're going to have to do, we're also going to have to do derivative of 3x squared on the bottom. Derivative of the 1 is a constant, so that'll be 0. So bottom's going to be 6x. All right, so then derivative of the top. This part we will probably want to think of here as kind of like chain rule now. So secant squared of x is really like this. So applying chain rule, bring down our 2. Leave the inside alone, secant x. New power is going to be 1 on that, and then derivative of the inside derivative of secant is secant tangent. And our derivative of R1, like we said, is a constant, that's 0. All right, so now just going to simplify quick. That means we got secant times secant to secant squared x times tangent x over 6x. All right, what do we get now if we plug in 0? Well, if we plug in 0 now, secant squared of 0, we already had that one before. That's going to end up being 1. Tangent of 0, that's going to be 0. Bottom's going to be 0 again. So we still have this indeterminate form of 0 over 0. But if we start applying derivative now, it's going to the top's going to start getting really messy. So if that happens, what you want to do, try to pull out what you can. Take advantage of some of those limit rules, because the limit of 2 things, if you're being multiplied, you should be able to kind of pull them apart, and they're still equal to the same thing. So the part in this that's giving us that the 0 part is on top. The tangent was 0, and on bottom is the x. So let's separate that out and split this into 2. So 2 secant squared x over 6. That stuff we can take out as one limit times limit of the same thing to 0 of just tangent x over x. This is the part right here that's giving us that indeterminate form of 0 over 0. So now let's apply Lapitals again here. So we're going to have a limit as, actually let's just do this here. We got Lapitals. Let's actually just figure out this part we should be able to figure out. If we plug 0 in there, it's just going to equal 2/6 times. Now let's apply Lapitals to this. Over here, derivative tangent secant squared, and derivative the bottom is 1. Now if you plug 0 in for that, we should be able to get our answer here. So we get 2/6 times secant squared. As we go to 1, remember that's 1 over cosine, that's just going to go to 1. And so our answer here is 2/6, or 1/3. Find the limit as x goes to pi from the negative side of sine over 1 minus cosine. Again, start by plugging in and see what we get here. So if we do sine of pi and sine of cosine pi, what do we get? On the top sine of pi, that's our y value. That's our y value when we're here. Well, that's going to be 0. On top we get 0. On bottom, cosine pi, that's our x value when we're here, and our x value would be -1. So on bottom we got 1 minus -1. Do we get an indeterminate form here? Actually, no, we don't. So if that happens, then don't apply Lapital's rule. Here we just get 0 over 2, which would be 0. So if it's not an indeterminate form, don't apply Lapital's rule to one that does not end up being either 0 over 0 or infinity over infinity.